Just checking on the audio channel. They're all good. Sharing the screen. Go. Right. So let me move this out because otherwise it gets recorded. It occupies a block on the screen that is nothing can get through. And we got people signing in. Okay. All right. Okay, so let's get started. So we are switching back and forth a little bit today, because the first part of this class is to give you the solution of the homework assignment. I'm guessing that some of you are interested in knowing what the solution is and how I do the derivation. So that's the first thing we're going to do. The recorder is on right now, so you guys can actually watch the video also. But having your own backup on your phone, it's okay. It's just interesting watching you guys here holding up a phone because it's all getting recorded. Okay, we actually have a backup because typically I will download the video from Zoom and then re-upload to YouTube. So I actually have two places to get back to the original recording. Zoom is not very good with transcription. Google does a much better job with YouTube, but Zoom does a better job in terms of capturing the content. It's a higher resolution. So, I'm kind of using both at the same time as a trade-off. And then Zoom also allows me to kind of live cast at the same time. So that's the other advantage of using Zoom. All right, so we got one person who is participating remotely today. I hope that person can hear me. So, all right, so let's go ahead and get started. This is the original expression, this part here. And for those people who say, I don't want to look at disjunction as a plus, I don't want to look at conjunction as a multiplication. I am sorry, but it's going to be the representation we are using, going forward, just because it is a lot more compact and also it is easy to type on the keyboard. The disjunction symbol, even though it looks like a V, but it really is not a V, and so on. So this is the representation I'm going to use from here on. All right, from the first line to the second line, we got another person. There we go. So from the first line to the second line, from this line to this line here, I used. Probably wanted. All right, so from this line to this line here, I was using the implication definition. So that means this particular implication turned into, oh, this is not done yet. I was doing one at a time. Okay, so I only dealt with the first implication, which is this implication. It turned into an or, and in addition to turning the implication itself into an or, I also have to negate the left-hand side of the implication. So any questions about this step? Nope, we are good. All right, so from the second line to the third line, I also use the implication rule. I should probably be using this slide here. They look exactly the same because it's just plain text. So I also use the implication definition again. So this time I'm focusing on this particular implication and turn the left-hand, negate the left-hand side and then or the right-hand side. It's the same application. It's just nesting into the implication that is in the inner part of the original expression. So are we okay up to the third line at this point? Okay. So from the third line to the fourth line, I use EM, which is De Morgan's law. So in this case, I am looking at this negation, and I'm distributing that negation to the or that is inside the entire thing. So by doing so, I'm doing everything really, really step by step. So by doing that, I'm negating each component of the original or. This is being one component. This is being the other component. So each one is negated on its own. So now we have the negation of the left-hand side of the original disjunction And then we have the negative version of whatever is on the right-hand side of the original disjunction. But we also have to make sure that we change the disjunction into a conjunction, which is invisible here because it looks like a multiplication. So that's one application of De Morgan's law. And then the second application of De Morgan's law is looking at this particular expression, because this is a negation. This is a negation applied to a conjunction. And as a result, I can apply De Morgan's law again. And the result of applying De Morgan's law is distributing this negation to Q. So Q becomes not Q. We also distribute this negation here to not S. So not S becomes not S. I do not even bother to kind of collapse the double negation into nothing because I want to separate those into different steps. So are we still doing okay so far on line 5? Okay. So De Morgan's law and the application of the definition of implication are unavoidable. They have to be performed simply because in CNF, there's no implication. So you have to get rid of implication. And also in the CNF, the only thing you can negate would be a single variable, which also means you cannot have a negation of an and or the negation of an or. So De Morgan's law has to be applied. There's nothing that you can do to avoid the application of De Morgan's law. Now, distribution is a little bit tricky, okay? Because you can do distribution in different ways, and sometimes it's easier, and sometimes it's harder to get everything into the conjunctive normal form. So from the 5th line to the 6th line, it is a simplification because I look at the double negation here and go like, that is useless, okay? Because double negation cancels itself out. So it is, I just got rid of that. And then from the 6th line to the 5th line, I use distribution. So in this case, I'm using distribution on the left-hand side only. And the distribution is looking at P and not R as one single thing. And it is distributed to not Q or S. Is that okay? So this is where things get a little bit tricky. So if you need a further or better explanation, I can do so. Are we okay with this particular application of distribution? We good? I can go over this one more time. And in addition, I can even tell you which distribution we are using. So let me get back on here and I will show you which distribution I was using. So I was using the distribution of A and B or C is the same thing as A and B or A and C. So that's the distribution that I am using. And what you need to do is to consider P and not R as A over here, and then not Q is basically B over here, and then S is basically C over here. That's the distribution that I use, because there are 2 rules of distribution in Boolean algebra, whereas there's only one in normal algebra. Is that helping? Is that helping to clarify? Okay. So this is symbolic processing, and symbolic processing is really important in computer science because after all, your entire program is turning how to do something into symbols and statements. So symbolic processing is really kind of critical in computer science, generally speaking. And we have one more person joining us. There we go. All right, so now we got a question. Yes, go ahead.
Sorry, I'm trying to figure out this different, but when you're finished doing the definitions of your implication, shouldn't it be not two parentheses, not parentheses, not P or R parentheses or P not that? But I feel like the second definition of that.
You mean this line does not look right to you?
Yeah.
Okay, well, let's take a look, okay? Because it is possible that I might have made a mistake.
Not two parentheses, not parentheses, not for how I have it, and then the rest is same.
The rest of the same?
Yeah, but this is that first part.
Okay, so this is the line where my expression is different from yours, you know, the highlighted portion? Okay. All right, so let's take a look and see if I made a mistake. Okay, so the first thing we need to do is to find out what this negation is being applied to. And this is basically a matching of the parentheses. So this negation here is applied to this entire thing. And the conversion is taking P implies R into not P or R. That's the only change between these two lines. So I'm not spotting any problem because the implication means A implies B turns into not A or B. And in this case, P is the A and then R is the B. So I can kind of try to clarify a little bit more here because A implies B is the same thing as not A or B. Does that help or? Okay, so maybe after class you can show me what you have. It is possible that you have exactly the same thing. It's just that the way you group the parentheses, which I can't really catch audibly. It's that's on me. Okay, I'm just not a very auditory person. But after class you can show me and I can definitely take a look. All right, so we have distribution and then we have distribution again. And this time I'm going to have to kind of reduce the size of the font because otherwise we cannot see the entire thing. So from here to here, it is distribution again. And the distribution in this case is doing a FOIL on this side here. So we have 3 terms in this conjunction, and then we also have 3 terms on this particular conjunction. So when we do a FOIL, which is also a Cartesian product, right? Because we match each one on that one side to each one on the other side. So functionally speaking, it is kind of like a Cartesian product. So we end up with 9 terms. So the P and the P groups into this one, the P and the R, not R, group into this one, the P and the S groups into this one. And then we take a look at the second item of the left-hand side. That once again is that Q is grouped with P. So we have P or not Q, excuse me, with the not Q here. And then we have not Q grouped with the R. And then we have the not Q grouped with the S and so on. Okay, yes, it is mechanically very tedious, but it's doable. Okay, even by hand, it is doable. So basically we end up with 3 times 3, which is 9 items out of the FOIL operation. Is that okay? Does everybody understand how I perform that particular distribution? It is ugly, okay? It is tedious, but it is doable even by hand. Any questions? Are there any questions about how I ended up with this particular expression? No questions? We are good? Okay. So the next one is instead of doing another FOIL again with these two, I just go like, okay, let's do some simplification first, okay? Because after simplification, maybe things will not be as insane. So I do some simplification, actually not a whole lot. P or P is simplifying to P all by itself. Okay, that's one, and that is that's not the only one. I got another simplification somewhere, which is the not R or not R simplifies to only just not R. So those are the 2 places where I did the simplification. The simplification is based on A or A is the same thing as A. Are we good so far? All right. So once we have the simplification, I do the absorption. And this topic here, this rule was introduced in the previous lecture. I talked about it without knowing the name, and I thought, okay, I think it had something to do with absorbing something. And then Omer, looked it up and and reported back and say, oh, according to ChatGPT, I still remember that. According to ChatGPT, it is called the rule of absorption. So the rule of absorption allows us to do quite a bit of simplification, because as long as we have P all by itself in a conjunction, any disjunction as a term in the conjunction that also includes P, they are all going away. Okay, because if P is false, okay, if P is true, then all of those will be true automatically because they are all disjunctions, including P itself. But if P is false, it doesn't matter because this is the one huge big long conjunction. If P is false, then the whole conjunction is going to be false anyway. It doesn't matter what P is ORed with as one of the terms inside the conjunction. So does that make sense? Does it make sense in an intuitive way?
Could you state the rule again? Could you state the statement, the first one that you said?
It's really hard for me to roll back because once the words come out of my mouth, I lost.
Okay, so what is absorption?
Absorption, okay. So I can describe absorption in here, okay? So absorption means, if you have a conjunction and the conjunction has some term A here, some expression A, it also has a different term, which is a disjunction involving A. This whole thing really just boils down to A. That is basically the essence of absorption in this particular application of absorption. Okay, first of all, does that make sense, right? Does it make sense? When A is true, then A or B is also automatically true, which means it is the same thing as A, which is true. So what happens when A is false? If A is false, then the entire conjunction involving A is going to be false anyway, which is also making the left-hand side of the equality the same thing with A itself. So without even using a truth table, just by understanding how conjunction works and how disjunction works, we have already proven that A and A or B in parentheses is really the same thing as A. The A or B inside the conjunction does not do anything useful at all. So it can be simplified out, which basically makes this the absorption rule.
Is this the only?
Absorption?
Yeah, this is the
No,
only.
that's a separate one. We'll see whether I use the other absorption. No, I guess not. So the other absorption applies when you have a disjunction as the overall operation, and then you have a conjunction involving a more complex term compared to another component inside the disjunction. So it works the other way too. Okay, I can write this here, but it's not going to be the one that I'm using here. Okay. So we have A or A and B in this case, and I claim that this also is really just A. So you can prove this using a truth table that has 4 rows because A and B are independent variables, and you can just work out all 4 rows and say, oh, okay, they boil down to the same thing. But you can also try to look at this from a intuitive perspective, which means what happens when A is true? Okay, when A is true, then A is going to be true. A and B may not be true, but I don't care because this is a disjunction here. If A is true, then the whole disjunction is going to be true, which means A equals to A because A is true. So now you say, what happens when A is false? If A is false, then A is false. But A and B is also automatically false without even knowing what B is, because it is a conjunction. If at least one side of the conjunction is false, the entire conjunction is going to be false. So that means, when A is true, the left-hand side is going to be true. When A is false, the left-hand side is also going to be false. So now we have intuitively explained how that works. Now, if the intuitive explanation doesn't work with you, because some people really prefer to mechanically see the actual proof using a truth table, you can work out the truth table. It will work out exactly the same way as what I just talked about. In other words, the value of B does not matter in either of these equalities. It's just that in this specific case, I applied the first version of the rule of absorption and not the second one. Is that helping?
Oh, yeah.
Okay.
Yeah.
All right. So you can see how the rule of absorption is really helping us in this case, because anything in the conjunction that has P as a component, they are all redundant. Okay. So they all go away. So this one goes away. The next one goes away. The one, also goes away. And then this one goes away. And then anything that has not R in it is also going away because we have not R all by itself here. So any disjunction inside the conjunction that has not R as a component, they also go away. So that means a lot of them go away. This thing is gone already. We can now throw this one out as well. We can throw this one out also. So we did a lot of simplification because of the rule of absorption. Are we doing okay so far? Are we understanding how we got from this really messy thing? Okay, let me highlight what messy thing we're talking about here. And we boil it all the way down to something that is far more simple. Or simpler. Are we good? Okay. So now what do? We apply distribution. So this particular distribution is looking at this entire thing as one thing, and then we are distributing over this side over here. So let me add a description of this distribution. So we are basically looking at A or BC, and that is the same thing as A or B and A or C. That's the distribution that I applied going from this particular expression to this particular expression here. Are we doing okay so far with this? Yes or no? Okay. So, yeah, I'm not seeing any questions. All right. So once we have this, then I apply distribution again, and this particular distribution, the next distribution, is based on the same thing, if I would see it correctly. Yep, it is. So let me explain again which distribution I'm using here. It is also using the same distribution, which is it's the same thing, even though it looks different, because this time we have BC plus A, or B and C or A. It becomes B or A and C or A. There we go. So are we still doing okay so far? Question? Nope. Oh, okay. All right, so after two distributions, we end up with this big mess here. So because the homework assignment only wants to get to a conjunctive normal form, which means we have a huge gigantic conjunction, and then each item we are ending is by itself a disjunction. And the only thing we can have inside the disjunction would be variables, PQRST, or the negation of a single variable, PQRST. So technically speaking, after I apply the associated law, which basically just dissolve all the parentheses, I am technically done. If I turn this in, I should get full credit. But I'm not stopping there because I can see some opportunities to simplify. And even the last line, if I remember correctly, you can still simplify a little bit. We'll get to that when we get to that. Okay. So I simplify a little bit because I recognize that we have R or not R here. So it doesn't matter what the value of R is, okay? The expression of R or not R has to be, it has to be true, it has to be one, because if R is false, then not R is going to be true. If R is true, then we are good, right? So that simplifies to just true. So that's why we got a 1 over here. And a 1 or true inside the conjunction does not do anything useful, because anything and true is just that anything. So that means we can simplify that out as well. So we end up with this final answer over here, like this. I'm looking at this and I'm thinking, can we simplify this any further? Particularly using absorption, I don't see any way to simplify this any further. So this is the final answer. All right, so questions? Go ahead.
This is like last time when you showed an example, you showed like
Oh, it was okay to like simplify it to a certain point. Putting it down further. Is there any point to doing that here, or do you always want Azure?
Well, I want the answer to be a CNF that is equivalent to the original expression. So to get full credit, that is needed. Now, if you do some derivation, it kind of depends on which direction the derivation is taking you, because there are some derivations that are useless. And if the derivation itself is incorrect, then I cannot give partial credit, even when there are derivations, because if they're incorrect, they are incorrect. Does that answer your question?
Yes.
Okay, very good. All righty. Yep.
So, if you did it like a slightly different way
Mhm.
and you got a different like final answer, but the truth table matches, is that still correct?
Yes, that would still be considered correct. So to get full credit out of this particular homework assignment, there are two criteria. The first criterion is it has to be CNF. The second one is it has to express exactly the same truth table as the original expression, which is up here. So as long as you meet both of those requirements, you would get full credit, even if your final answer is not quote-unquote optimal. Yes.
Is it possible to get something else as the result of the Boolean?
It can look different.
Yeah.
It can look different because you may not, some people may not have done the absorption. So you might have some additional terms that really do not need to be there. But it's not wrong either, because they simply do not add anything to the truth table. So the bottom line is, does your answer generate the same entries in the 32-row truth table? If the answer is yes, and it is also in CNF, then your answer will still be correct. And even, yeah, go ahead.
So my answer matches or has the same truth table, but
Mhm.
it doesn't have the P or not.
Does not have the P or not T.
Yeah, so I think it can. I'm not sure how.
That I do not know. You might have another term that has P and not T in it. Maybe you have some additional items inside that particular disjunction. No.
I think the P or not T is redundant because the P or R and the not R plus.
Oh, yeah,
Or
yeah.
not.
I see what you mean. So basically, there's a way to apply De Morgan's law, I mean, not De Morgan's law. It is the result of this thing being resolved with this thing here, and the end of that resolution is this thing here. So this term is implied by the conjunction between the first term here and also what I see as the last term over here. So that's fine. I understand that. Yeah. So that means your P or not P is not needed here because it is implied by the conjunction of this term and that. No. They are not canceling out. Okay, it is simply meaning that P or not P is implied already by the other two, and as a result, it does not add anything to the conjunction. So the conjunction is still evaluating to exactly the same truth table with or without P or not P in it. Yep.
So just in theory, we use resolution to simplify it.
It is not required. It is not required. See, a resolution is something that we want to do in the next homework assignment. So before we do the next homework assignment, or before I talk about the next homework assignment, I am going to take roll. So I think we have allowed people enough time to be here. Okay, and I'm looking for the browser window. Nope, not this one. Which one? Come on. There we go. All right, so let's go back to here. And then the row ticking activity has today's date on it. You cannot see it just now, you can see it. So go ahead and refresh your browser on your mobile device and then go to the 2023 March 29th row ticking activity. And the word is permit. So I'm gonna, I'll just show you because the people online cannot see the whiteboard. Right there. That is the row-taking word, which is PERMUT, which is the name of the function to calculate the number of permutations in the spreadsheet. Righty.
This is permit.
PERMUT permut. Yep. Which is the abbreviation of permutation. Righty. Okay, looks like, does anyone need more time? Okay. I'll just write it on the whiteboard so we can that part. And I don't hear anyone from the remote participants, so we're going to continue to talk about the next homework assignment. I think some of you may like it and some of you may frown when you see the next homework assignment. That's a usual thing in my classes. All right, so this one is giving you the solution, and you can simplify that if you want to. You can take out P or not P, if you want to. It doesn't really matter. It doesn't change anything. So this time I want you guys to perform proof by contradiction. The first theorem or proposed theorem is this expression here. And then the second proposed theorem is this one over here. So what you need to do, okay, you guys will remember what is proof by contradiction. Yes or no? Okay, all right. So what I want to do is to tell, okay, so I will refer to these things, in Greek letters first, and then we'll go back to proof by contradiction so that we can talk about what to do in proof by contradiction. This is your psi, okay? And this is your phi, okay, which is the theorem to be proved. So this is everything that is known to be true, which is also, you can consider this a conjunction of everything in iota, okay? That's the first thing that's given to you. And then the second thing, for each step, this is phi, which is the theorem, the proposed theorem. And your job is to prove whether this is indeed a theorem or not, based on what you're given with that is true to begin with. Okay, are we good so far between what is psi and what is phi? Okay, psi is everything that is known to be true as a conjunction. And then phi is an expression that I want you to prove whether it is a consequence or whether it is implied by psi or not. Are we good? Okay. So now we go back to propositional logic and we track down proof by contradiction. So I'm too lazy to find it. So we'll just go ahead and search for it. And there we have it. I'm going to get rid of the highlight. Okay, there we go. So this is proof by contradiction, and all we need is to get to here. So this side is representing the result of the discussion today, which is that conjunction CNF that I gave you. You can start with that. This is the phi, and you are given two different phi's in your homework assignment. Okay, so there are two basically. There are two things that you need to prove. So if this conjunction leads to a zero, it basically implies your phi is implying phi itself. And this is what we want, okay? But when this happens, okay, when psi and the negation of the theorem, the proposed theorem, is implying false, then what does that actually mean? Well, what that means in this case is this conjunction itself has to be false. Is that okay? Oh, yeah. That's the first thing you need to do. So that means that whatever expression I gave you as phi, whatever expression I gave you as the proposed theorem, negate it first and then turn it into its own CNF. So once you have done that, then phi is a CNF. Not phi is also going to be a CNF. So what can you tell me about the conjunction between two CNFs? It has to be a CNF, okay? So when you merge two CNF by conjunction, then the merged expression is a CNF. Is that okay? So that's the first step, okay, is to create that really rather long CNF. And then the second thing you need to do is to basically repeatedly do something until you either arrive at a contradiction or there are no additional things you can derive from it. That portion has to do with resolution. So we go back to resolution. This is resolution, or at least the theory of resolution. So in your case, what you'll be looking for is in a disjunction, you're looking for two disjunctions where one has the non-negative version of a variable and the other one has a negative version of the same variable. When that happens, you can concatenate the rest of both of those expressions and do not need to mention the variable that is negated on one side and not negated on the other side. Are we good so far? So this is a reminder, okay, because we talked about this already. And in previous lectures, we also talked about an example. And I know many of you might have forgotten about the example already. So we're gonna go back to the example so I can illustrate what it means, okay? So we'll go to the example portion, okay? And here we have an example. So in the example, we first convert, this expression into a CNF, which is this result here. And then later on, there's another exercise. And we want to okay, excuse my, there we go. Okay, so there are two examples here. So in this particular example, psi, which is everything that is given to you that is true to begin with, converts into this particular CNF. Phi, which is the proposed theorem, is, start with this, and you have to negate it first, and then turn it into a CNF, and it turns into this particular CNF. So when you have a conjunction between psi and also the negation of phi, which is this one here, then you have this, what I would usually call a super CNF. It is basically just the conjunction between the CNF representing psi and the CNF that is representing the negation of the theorem that is being proposed. So now the question is, when I look at this, can we apply a single step of resolution? So how do we apply resolution? We need two disjunctions, one mentioning a variable, the other one mentioning the same variable but negated. Okay, so we can take a look. Okay, the systematic way to do this is to start with the first disjunction, and then you ask, do I see anything that has P in it, not negated? No, no, and no. Okay, so that means we cannot use not P any resolution. Then we look at R and we ask, do we see any not R in the other disjunction? Nope, nope, and nope, right? So that means the first disjunction cannot resolve with the rest of the entire conjunction. And what do? You do it quote unquote recursively, which means you look at the rest of the conjunction and you do exactly the same thing. So you look at not P or not Q, and then you ask, do we see P inside any of the disjunction all by itself? The answer is no and no. Okay, and do we see Q non-negated? No and no. So now we look at the rest of the expression, which is not P, and we're looking for T in the rest of the CNF. Nope, and we're done. So this particular super CNF cannot resolve even a single step. So that means we cannot get to false. If we cannot get to false, it means the original phi is not a given. It is not implied by psi. Are we doing okay so far with this? Now, this one is a little bit tricky because I'm not showing you how resolution actually happens, but I'm showing you how it does not happen. The next example is based on the same side. So basically, we are using the same side that we have derived up here, but this time phi is different. So this time I have phi prime just so that I can refer to the two proposed theorems differently. So this time we have phi prime being P implies not Q. And once again, we have to negate the proposed theorem first. So negate the entire thing and then turn it into its own CNF. Is that okay so far? Okay. And then we have a super CNF again. This is my mess up. I should have used a backslash so it shows up as a Greek letter. So now we have a super CNF with psi, everything that is known to be true, and the CNF representing the negated version of the theorem that we want to prove. So this portion here up to here is corresponding to psi. This portion here is corresponding to not phi prime. Are we still doing okay so far with those Greek symbols? Okay. So now the question is, can we apply resolution? So once again, use the systematic approach. Okay. If this is the first time you're doing it, I would suggest using a very systematic approach. So we look at not P from the first disjunction and we say, do we see any P down the line? Oh, we actually do. Okay. So that means, I do not actually follow my own advice because R would have become a new term in the conjunction. Is that okay? Does everybody understand why R can become a new term? Okay. So let's take this one. I'm trying to determine how to explain this. Let me switch back to Joplin. And this way I can use Joplin for that explanation. So we have text here. And I need to copy this whole thing. I'm just thinking about how to copy this. I suppose I can just write it out. We have not P or Q or R. Okay, so then correct it. Not P or not Q, not P or not Q. And then we have P by itself, and then we have Q by itself. This is the original super CNF. And now I need to indicate how we perform the resolution. So I'm going to use a really crude way of indicating which variable I use as the quote-unquote connector between the two. So here we have not P, and then here we have P by itself. Now you look at this term here and you go like, hey, that doesn't look like a conjunctive disjunction because it's just P all by itself, right? So what is the cheapest way to turn it into a disjunction without changing the value of the original expression? P or false. Okay, because anything or false is the original thing. So are you happy here now? You're looking at this like, oh, okay, so it is a disjunction, right? So as a result of the resolution, what we do is we end up with basically the left, whatever is left over between the two expressions. So when we look at the first expression, which is not P or R, we look at the second expression, which is P or false, then we eliminate the variable that is acting as the quote-unquote connector. In this case, P as well as not P. And then we use the rest, we concatenate the rest to become the new expression. So in this case, when you look at the rest, we simply end up with R coming from the first disjunction, and then we end up with 0 or false from the second disjunction. Is that helping? Okay, all right. So we can perform a few more steps here. So it's going to be helpful for that with that. So now we look at the first expression again, and we ask, cannot P be used again as a connector for the rest of the conjunction? The answer is no. Because the not P cannot resolve with Q, okay, not P cannot resolve with R, so we are quite done here with the first disjunction. Yes,
Does it have to take the not P from the R and E together from the not Q?
oh,
Or
I'm not
Q?
sure what you're asking.
Sorry,
Can you
no,
repeat
does
the
it have to be
question?
the first not P or can it be the second not P?
Well, I'm not quite done with the first not P or R yet. So when we move on to the second not P or not Q, we can resolve again. I'm doing this in a very, very systematic way, okay? I'm not even done with the first disjunction because the first disjunction also has R in here. So the next question is, can the R coming from the first disjunction resolve with anything after that? The answer is no, because if the first disjunction has R in it, then we are looking for a not R in the next disjunction that we want to resolve with. We look at this one, it does not have a not R in it. This does not have a not R in it. This does not have a not R in it. This does not have a not R in it. So we are now officially done with the first disjunction in the conjunction. Is that okay? So now we move on to the second. And we see not P again, we go like, oh, okay, I know what to do with not P. We just have to look for P in one of the other disjunctions. So we look at that and go like, we find it right away. Is that okay? Do you see how I'm finding the connector between the two disjunctions? And then the connector itself disappears, and then we concatenate the rest of each of those disjunctions. So now, what do we end up with? So let's check out. So it becomes whatever is the result of the resolution can be appended to the original conjunction because it is implied by the other part of the conjunction. So now we look at this and go like, on one side we have not Q, on the other side we have just false in it. So now we have a new disjunction, which is not Q or false, that we can add to the original disjunction, or the original CNF. Is that okay so far? Okay. So now we systematically do it again. So we look at this not P and say, do we have any additional disjunctions that only have P in it? The answer is no. Okay, this one has Q in it, this one has R in it. So we are quite done with the not P of the second disjunction in the conjunction. So now we move on to, guess what? The not Q of the same disjunction, and we find a way to use it. So we look at this not Q and we ask, can we find Q non-negated in the other disjunctions? And the answer is yes, we find one, because this one over here is just Q by itself. So Q is becoming the connector between these two disjunctions. So once again, we do a concatenation, and then the concatenation can be appended to the original CNF. So can someone tell me what is the result of this resolution? Not P or false, okay? Or just not P, but we can always just add the or false because it doesn't change the meaning of the expression. Okay, very good. So now we are officially done with the second disjunction of the conjunction. So now we move on to the third one, which is the P here. And what do you think? This P over here, it cannot resolve with Q, cannot resolve with R, cannot resolve with not Q. But it can resolve with not P. Does that make sense? Okay, so we say, okay, this is a connector, and this is the other end of the connection. So as a result, now we have a new expression, the result of the resolution. What do you think is the result of this resolution? False or false? False or false. That is correct. So what is false or false? False. It is just false, right? Okay. And we are done. So now we have a contradiction because the conjunction between what is known to be true, which is psi, the Greek letter, and the negation of the proposed theorem, which is not phi expressed as a CNF, that super CNF is false. We have just proven that the super CNF is false. Now, if I go back to the notes, okay, what does that mean? It basically means this thing here is false. But according to proof by contradiction, that is enough that to conclude that phi prime itself, in this particular example, is implied by psi. And that explanation was, presented earlier that talks about why proof by contradiction works. So are we good so far? I know there are many components to this entire thing, but I'm hoping this particular demonstration helps you to make all the connections. Are we doing okay? Yep, okay, all right, excellent. All right, so you got 1 week to work on this one too. So, the first thing is, once again, turning something into a CNF. And then the second thing would be to do the resolution.
So what's something like in the real world that you prove that?
All kinds of stuff. So we applied proof by, okay, so are you referring to the proof technique of proof by contradiction? Or are you referring to the application of proof by contradiction in the context of propositional logic?
I think that when you say, okay, I need to prove something, I'll use this technique. What would think for that?
When a direct proof is hard. And there are many cases like that. Remember, we talked about the pigeonhole principle, right? The pigeonhole principle basically says you have more pigeons than you have pigeonholes. And when all the pigeons come home, there will be at least one pigeonhole with more than one pigeon in it. It sounds really reasonable, it's intuitive, but can you prove it using hard logic? And as it turns out, as intuitive as it is, using direct proof, it's really difficult on this one. But proof by contradiction makes it super easy, because what you do is you negate the consequence of the premise. In other words, you're keeping the premise, which is we got more pigeons than there are pigeonholes. But then you change the conclusion of saying, I'm pretty sure there's a way to arrange so that each pigeonhole only has up to one pigeon in it, right? Remember that example? And then we look at this and go like, wait, hold on a second here. So that means the total number of pigeons cannot be greater than the number of pigeonholes, which means the number of pigeons is going to be less than or equal to the number of pigeonholes. But the premise is telling you exactly the opposite. So those two cannot be true at the same time, which means now you have a contradiction. The conjunction between, I'll address your question. So the conjunction between what you're given with and the conclusion of the negation of the conclusion, leads to a contradiction, which is basically false. And therefore, using the technique of proof by contradiction, we know that the pigeonhole principle is correct. It is true. So that is one example, and there are many other examples I can use. I can illustrate with that as well. Yes, go ahead.
So you're taking the thing, you're creating a theory based on that. So you reverse the theory.
I'm not reversing, I'm inverting it.
You're inverting the theory.
Yep.
And then you're proving that the theory is false.
No, I'm proving the premise, what you're given with to begin with, and as a conjunction, the negation of the theorem has to be false. Which is not to say the negation of the theorem itself is false. It is saying the conjunction between what you're given with to be true to begin with and the negation of the theorem, that conjunction has to be false. I know it sounds like I'm splitting hair and then splitting it again, but it is very important in this class that I do that. I know it sounds annoying to some people. Yes.
So to have the theorem be invalid, you have to not be able to do resolution, or can you still?
That is correct. So if you get to the point where you cannot resolve any further, like this one here, and yet you're not getting the zero, the false, that means, whatever phi in this case to begin with is not implied by psi. That's all you can say is it is not implied by psi, but you cannot say whether it's true or not.
So could you still do some type of resolution and not get that zero, that false?
That is correct. Sometimes you have to do a lot of resolution and then only to come to a dead end is like, oh, but yes, that can happen. This is just a very oversimplified example of a dead end.
How can you relate that? Supersede that? Like, what is it valid? How can you relate to that to the pigeonhole set?
So I cannot relate directly because the pigeonhole principle is not expressible as propositional logic, at least not easily. Because it involves algebra, normal algebra, right? And in this case, there's no provision to actually use normal algebra in this case. But if you want to look at, not so much the resolution side, then proof by contradiction applied to the pigeonhole principle, we basically have psi representing there are more pigeons than there are pigeonholes. The negation of phi is basically saying the conclusion of the not phi is to say there's at the most one pigeon in each pigeonhole. And then the conjunction is basically saying, okay, can these two things both be true at the same time? And then using algebra, we show that it is not possible. But we did not use resolution in that case to prove the theorem. Is that okay so far? Yes? No? Do you guys ever wonder what P, Q, R, S, T can be? We only know those as Greek letters in alpha, and they are known as variables. So what do you know what each one represents? What is a Boolean variable? What in real life, okay, how do we apply this? So I'll give you an example. Okay, this is going to be fun. So we can say P as a Boolean variable is really just saying Tack is a good professor. Now, I'm not saying that I am a good professor. Tack is a good professor is a variable, which means it can be true, it can be false. We do not know what it is. Okay. And then we can say Q is Professor Hermelin is a good professor. Am I saying that he's a good professor? No, I'm saying it can be true, it can be false, right? I can say S is, okay, this is where it doesn't really work because the quantifier, if we can say one of these two professors is a good professor. So that means that P or Q is known to be true. So P itself does not have to be in iota. I don't have to say that Tack is a good professor. Q does not have to be in iota. It may not be known that Professor Hermelin is a good professor, but I can put P or Q in iota, which means at least one of us is a good professor. Is that okay? So that's basically what P, Q, R, S, T are all representing. Each one is representing a statement that can be true or false. But that statement doesn't have to be a single value. If that statement by itself can be true or false, but there's no limitation of what that statement can involve. All right, so be okay with the next homework assignment. You have 1 week to work on this one. Okay, so once again, try to use my office hour. Okay, if you're stuck in the derivation, of the CNF, use my office hour because I can at least tell you whether you got it right up to that point or not. Okay, and if you want me to check that sort of stuff, you really want to turn in your expressions in this particular format because guess what? I got a tool to do it. I'm not going to do it by hand, but if you give me expressions in this particular format, I have a program that can say, yep, these two are the same, or these two are not the same, which is what I can relay to you, is whether those expressions are the same or not. Yep.
Your office hours, because the kids changing around all the time, is the most recent one on meeting announcements?
In the syllabus is up to date. Yep. All right, so we are getting back, remember I said earlier that we're gonna flip-flop between propositional logic and also counting. So we are now switching back to counting. So let me go back to the modules, and I think I might still have those modules up. Counting, there we go. Okay, so what we'll do today is to start with the actual terms of counting or combinatorics. A trial is a single attempt to do something, typically involving choosing something, and a trial has outcomes coming out of a trial. So I'll give you an example of what a trial may look like. Oh, the next paragraph says the trial has a set of possible outcomes. So a trial can be flipping a coin, okay, the result of flipping a coin. So what are the possible outcomes of flipping a coin? Head or tail, okay, very good. If you have a six-faced dice, throwing the dice once can be considered a trial. So what are the outcomes of throwing a six-faced die? 1 to 6. There are 6 individual outcomes in that set. Okay, that makes sense. I have a bag with 60 marbles, okay, and they're all distinct. So what is the number of outcomes of picking one marble out of the bag, which can be considered a trial? There are 16 possible outcomes. So each unique marble in the bag is a outcome. Okay, so that's good. So once we define what a trial is, an experiment is nothing more than just a sequence or a series of trials where subsequent trials may be affected by earlier ones. And an experiment has its own outcomes. Okay, so what does that mean? Show you a few examples. And the first one is, okay, let me go back to Joplin and I'll use Joplin for that. Okay, so we'll go ahead and take a look at flipping coins. Okay, flipping coins. And we'll flip the coin, let's see, 3 times. Okay. So each trial is flipping the coin once. So in that case, the outcome set is, I'm just going to use regular and non-formatted math stuff here. So it's either head or tail. So are we doing okay so far with this part here? I'm just going to zoom in a little bit. Are we doing okay so far with each trial being flipping the coin once? The outcome set is head or tail. Okay. So now the question is, what about the entire experiment? Because this experiment is flipping the coin 3 times. So what do you think would be the outcome set of the experiment? Outcome set of the experiment. So what do you think that's going to look like? Yep, so we can. So I'm going to use a shorthand here without using the parentheses. So we can have head, 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 right? Head, head, tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and finally tail, tail, tail. Okay, so if you are looking at this and go like, that looks like a binary number. It looks like we are dealing with a 3-bit binary number going from 0, 0, 0 to 1, 1, 1. So a head is kind of like a 0 and a tail is kind of like a 1. You're absolutely correct. Okay, that's exactly how I derived these outcomes for the entire experiment. Is that okay? All right. And this is going to come back and haunt us a little bit later on. Okay, the way that we look at the 2 possible outcomes in this case. So we'll look at another example. Okay, so TAC has a bag of marbles, and the marble would be we can use the colors, right? RGB. Okay, red, green, and blue. Okay, so I got 3 marbles in my bag, and each trial is picking a marble from the bag, okay? So now the question is, what is the outcome set of choosing? Oops, yeah, go ahead.
Are you putting the marbles back in the bag after you?
No, we are not.
Okay.
Choosing one marble out of the. Oh, sorry, I just made a mistake here. Two marbles out of the bag without replacement, which means once you take a marble out of the bag, you do not put it back into the bag for the next trial. Are we doing okay so far? So that term is called without replacement. Yes.
Is there only one, there's only 3 marbles in the bag, 1 green, 1 blue?
Yep, that's the original setup. So we want to look at the outcome set of choosing 2 marbles out of the bag without replacement. And because I'm putting the marble into a tube, so ordering becomes important, okay? Because I need to know which one goes into the tube first, okay? So we'll just say ordering is significant. So now we want to look at this particular outcome set. So can someone tell me what the outcome set is going to look like?
Red, green,
Okay, red, green,
then red, blue,
red, blue,
then green, red,
green, red,
then green, blue,
green, blue,
then blue, red,
blue, red,
then blue, green.
blue, green. Yep, that is correct. So the outcome set in this case, there are 6 items in it because ordering is important. So we can choose the red marble first. That means that the second marble that we take out of the bag is either the green one or the blue one. Or we can choose the green one as the first one, then the second marble can be the red or the blue one. Or we can choose the blue marble first, then the second marble can be the red or the green one. And therefore, there are 6 of these, okay? Now, there's a very systematic way to generate this particular set. We'll talk about that later. But at this point, we just want to know what is the original set. What are we doing for each step or each trial? Do we have replacement? In other words, once we take something out of the bag, do we put it back into the bag before we choose the next marble? And is ordering important? Because whether ordering is important or not is has a lot to do with the outcome set. So to understand that part, let me set up another experiment. And it is very much the same as the original one. So once again, oh, where's my cursor? Ah, where's my cursor? My cursor disappeared. Oh, it's because I typed colon. There we go. All right. So once again, we have a bag of marbles. So once again, we have RGB, red, green, blue marbles. And once again, each trial picks a marble out of the bag without replacement. Okay, so it sounds like we have the same thing here. And this time, I want to look at the outcome set of choosing 3 marbles, okay, out of the bag without replacement. That's kind of redundant. We said that already. But this time ordering is not important. So the question is, what do you think the outcome set should look like in this case? This is a trick question. Okay, I have 3 marbles in a bag. I'm taking 1 marble out of the bag for each trial. We have 3 trials. But this time, ordering is not important. The only thing I really care about is, did I choose that marble out of the bag? So what do you think the outcome set is going to look like this time? It's just red, green, and blue, okay? But in this case, should I use a tuple approach, RGB in a tuple? It is a set. That is correct. Because I don't care about the ordering, which means it is a set because there's no intrinsic ordering of elements inside the set. The only thing that matters in a set is that a member of the set. But within the members, between the members, there are no implicit ordering. All right, so are we doing okay so far with, the concept of what a trial is, what an experiment is, what is the outcome of a trial, and what is the outcome of an experiment? Yes,
That is the set of one element that can be the set of arguments.
that is correct. So the set of outcomes. Okay, let me, this is the outcome set. Is a set that has one single element, but that one single element by itself is a set of 3 elements. That is correct. All right, so with this all said and done, the next thing we want to do is to say, okay, so we did everything like this by hand. So is there a programmatic way to do so? Okay, what do you guys think? This is a computer science class. If it's a computer science class, we want to, be able to programmatically do something. So the next chapter here, or the next section, talks about general counting, which means we are only concerned about the cardinality. So I'm going to skip that for now. Okay, we'll jump all the way to how do we generate the outcome set. Okay, so we'll just go ahead and get some exposure first, and then I'll double back to talk about counting, and then come back here later on, maybe sometime next Wednesday sounds about right, is the right time. So we are looking at a definition of omega. So we are going to use omega I to represent the outcome set of an experiment that has I trials. The first trial starts with the set T of outcomes, and we take one thing out of T for each trial without replacement. And we want to know what is the outcome set of this particular experiment, and ordering is important in this case. Okay, so does everybody understand what omega I of T is representing? Yes or no? I can describe it again. Yep. One more time. One more time. Okay. So we are concerned about an experiment. I is representing the number of trials in that experiment. Okay, so that's what I is representing. The set T is the outcome set of the first trial of the entire experiment. In other words, if we are taking marbles out of a bag, T is basically saying what marbles are in the bag initially. Is that okay? I is telling us how many times are we taking marbles out of the bag. I'm using omega here, and this is basically saying that the ordering is important. Did I choose a red marble before the green one? That is significant. Which one I chose first? So is that answering your question? Okay. So the result of omega I of T is going to be a set. It's going to be a set of tuples, because because sequencing, ordering is important in this case. So what I want to do is to say, can I mathematically define, how omega I of T is going to be calculated? The answer is yes, I can do that, and I can do that recursively. Okay. So the first thing I do is to ask a trivial question. So what if tag is tricking you and giving you an empty bag and ask you, how many ways can I choose nothing? Can I choose marbles out of a bag of nothing? The answer is there's one way, which is surprising, right? Because you think there's no way, but there's actually one way. So if you think about this as this is a bag which has no marbles in it. This is a tube, and I'm asking you, just pick your marbles one by one out of the bag and put it into this tube, and show me how many different ways you can have content in the tube. That is what it's asking. Yes.
Is there 0 trials to do it, or 1?
It has 0 trial. Oh, yes, you're correct. So this time your T doesn't even have to be empty. I can give you a bag of 200 marbles, but I'm saying you have 0 trials, which means don't pick anything. On the other hand, you're holding a tube, okay, where you're supposed to put the marbles into. And I'm asking you, so how many ways can you come up with the tube after the entire experiment? What do you think? There's one way to end the entire experiment, which is basically saying, tag, the tube is going to be empty, because you told me not to do anything. But that is a outcome, okay? It's just that that outcome has nothing in the tube. Are we doing okay so far? Yes.
So how you would say that, omega zero t is equal to set is one element, that element is a,
Empty tuple.
just because you're.
It is a tuple, it's just empty.
Yeah.
You can consider the empty tuple the same thing as a no string, which means it is a string, except the only thing in the string is the no terminator itself, so it has actually no content. Yep.
I was gonna call it, I don't know, zero two,
Say that one more time.
a zero two.
A zero tuple.
I don't know if that was the term. That was the truth, so, but
It's an empty tuple, which is analogous to an empty set. It is still a tuple, except there's nothing inside the tuple. But is that okay? It's a trick question, but nonetheless, it has an answer. So this is the end of the recursive definition, is when you have no trials left, okay? Then you can report back and say, heck, the only outcome out of this experiment is the tube remains empty because you told me not to choose anything and put it into the tube. Is that okay? All right. Yes, go ahead. You got a question?
For the empties set, is that what T is, or is that what the entire thing is?
Omega zero of T is the outcome set of the experiment.
And you would define T elsewhere. For T.
T would have to be given to you
Okay.
initially. That's why it's a parameter. All right. So now the next question is, what if I give you I trials? In other words, we look at this thing here. I give you I trials, okay, and you start with the same bag, let's say 200 marbles, and I give you 5 trials. So I'm asking you, what do you think is going to be the outcome set out of this experiment? This experiment has 5 trials. Each trial is taking 1 marble out of the bag and put it into the tube. And asking you, how many ways can you end up with the tube with marbles in it? So that's the question. Well, here's the answer, okay? The answer involves the big U notation. Do you guys still remember the big U notation? The big operator module that we talked about? Okay.
It wasn't big U,
Hmm?
it wasn't big U. We had pi, sigma,
Okay, all right, fine.
it's the same concept.
It's the same concept, yes, okay. So let's go back and revisit, the big V notation and so on. This is the big U notation, which means it is a big union of things. But what things are we unioning with? We are running out of time today. I got 2 more minutes. I'll tell you what I'll do. So what I'll do is I am going back to the big operator module. Big. I don't think it's in here. I think it's still in the announcement. I didn't put it into the notes. Or did I? Again? It's still in the announcement. Okay. So I will change that. I think it's in this one. All right. So this is the module that we talked about, in the other big operators. So I'm going to extend this one to include the big U and the big. Yeah, I think the big U is the only one that we need. So I'm going to include the big U notation here. So for those of you who are already understanding all of this stuff here and how things are being defined recursively, you can try that on your own, okay? You can say, okay, I'm going to take on this challenge and be able to try to express the big U notation using a similar method like this, using a ternary expression. So the question is, what am I going to use here? And what is the default answer? And what do I want to use as the recursive step? Okay, and I'll give you one more clue because this involves an element of. So that means, the notation of dx is going to be needed. Okay, remember dx is a function. As long as x is a particular set, d of x returns a specific element in x. And that's what it does, okay? So we'll go, we'll talk about this next Monday, so that we can look at the big U notation in this particular format. All right, you guys have a good weekend. I will see you on Monday, and don't forget the actual homework assignment, the resolution one, because that's going to take some time. So start as early as possible to get that one done.
I got the money.